I'd like to look at a couple of examples of coordination compounds, and there are three questions that I'm going to ask you about coordination compounds and when you see these on the test. First one is to draw the complex and include the charge on a central ion, draw an isomer of the complex, and then use crystal field theory to determine how many unpaired electrons there are. That's when we apply the D splitting stuff that we've already talked about. Alright, so the first thing we do is we draw a structure, and since we've got 6 things around the cobalt, we'll draw them in an octahedral type arrangement. And when we do that, we'll also have the Br negatives out here on the outside, and there's going to be 2 of those. So how do we find out what the charge on the central metal is? Well, what we do is we'll go over here. You can see we've got cobalt, and then 5 ammonias, and then a Cn, and all of that has to add up to positive 2. Now the reason I say positive 2 is because you've got -1, -1, so that's -2 on the outside, which means everything in here has to have a positive 2 charge, or it at least has to add up to positive 2. So since ammonia has a 0 charge, and we know what the charges are from back here, this table of ligands, most of them are negatively charged, but there's a couple of neutrals here as well. Those neutrals have lone pairs of electrons, but they're still not negatively charged. Alright, so going back to our calculation here. So ammonia has 0 and Cn has a -1 charge. So cobalt plus 0 minus 1 equals plus 2. So the charge on cobalt is going to be a total of plus 3. So there's our cobalt right there, plus 3 charge on the cobalt. That's going to be important for later. Alright, let's take a look at the next question, and that was to draw an isomer. Now this one was ripe for an anion exchange. Now you can only do anion exchanges if you've got anions on the outside and you've got something different that's negatively charged attached to the central atom. And the ammonias we can't exchange because those don't have charges on them, but the Br negative can exchange with the Cn negative, and that gives us this isomer here. So the Br is now attached to the cobalt and the Cn negatives on the outside. So this is an isomer of this particular compound. I want to point out that it doesn't matter where you draw the bromine on here. It's going to be the same compound regardless. Same with the Cn. It didn't matter where I put that either. So there's no isomerism going on there around the central atom. No positional isomerism. Just think of it like a sphere with a red dot on the outside of it. You can roll the sphere around, it's not going to change the nature of that sphere. Alright, so that's what's going on with that. The next thing we need to do is figure out the DD splitting that's going on here, and we do that by looking at the electron configurations. Now for that we're going to have to focus on the periodic chart. Now I want you to go back and think about your electron configurations you would have done back in Organic 1. And first of all, what I would do is find out what the electron configuration of cobalt without a charge on it would be. And the way we do that is we say, well, that's going to be the electron configuration of argon, so everything up to argon, that's a noble gas. We usually do it that way. So it's AR in brackets like that. And then 4s2, that's 4s1, 4s2. And then cobalt is here, and it's 1, 2, 3, 4, 5, 6, 7. So it's 7, and this is the D block right here. Remember, this is the S block, we got the D block, and we've got the P block over here. We're not too interested in the P's, but we go over here, and it's 4S because it's 1, 2, 3, 4 starts on this row, and D's actually start at 3. So it's 4S2 and then 3D7 down here. If you have doubts about finding electron configurations, go back and take a look at Module 12 in the Survival Guide, and that has a nice piece on how to do that. But just to focus on the D's, it'll always be 4s2 and then however many D's there are. If it was 5, then it would be there'd be 1, 2, 3, 4, 5. You'd end up here. So you can see how to do that by just by looking at the atomic number, and then that'll tell you how many D electrons there are. So it would be 26 minus 20 equals 6. That tells you how many D's there are. Alright, so that gives us that. Now for cobalt we've got Ar4s2 3d7, but we're not working with cobalt that doesn't have a charge, we're working with cobalt 3+. Now cobalt 3+ is cobalt that's lost 3 electrons. Now in this, when we're talking about compounds that we have metals where things are attached to them, what happens is the 4s2s are actually of higher energy than the 3ds. So the 4s electrons, the 2 electrons, they're the first to go. And then you've got one of the d's is going to be lost as well. So let me show you a picture of that. So when the cobalt is in an actual, we're going to ignore the DD splitting for now, but when it's in an actual compound, what's going to happen is you're going to have the 2 4s electrons up here, and then you'll have your 7 D electrons down here. So remember, I fill these in one at a time, and then I put the other 2 in. So there's my garden variety cobalt. Now to make it cobalt 3+, I have to lose 3 of those electrons, and the ones I'm going to lose first are the highest energy ones, and that's going to be the 4s electrons. There's your 4s, there's your 3ds. So the 4s, I take those 2 away, and then I'm going to take 1 of the d electrons away. So, and I took this one here, so I took that one and these 2, and it was 3+, so I had to remove 3 electrons. So now my electron configuration is Ar3d6. That's 1, 2, 3, 4, 5, and then 6. So that tells me how many electrons I'm dealing with in my structure. Now the next thing I've got to do is, well, I've got to apply the DD splitting, and if it's octahedral, which it is, then there's going to be 3 blocks down the bottom and then 2 blocks up the top. Now to decide how the electrons go in, I need to be careful about the whether it's strong field or weak field. So what I do, I go back up here and I look to see what's connected, and I had 5 NH3s and a CN, so I think we're looking at strong field ligands since everything's pretty much at this end of my table. So we're looking at strong field, which indicates that there's going to be a large energy difference between these 2 layers of d orbitals. So I've got 6 electrons to put in. I know that from up here it's 3d6. So I put 1, 2, 3, then 4, 5, and 6. I don't even touch these up here. I don't have enough electrons to do that. So what we end up with is a strong field situation or low spin, and we have 0 unpaired electrons in this instance. Alright, let's look at one more example. We've got a tetrahedral complex now. I know it's tetrahedral because there's 4 things attached to the central metal. We've got an I, a Br, an F, and a Cl. We don't care about the order or how they're connected around the chromium. They're all going to be pretty much the same, whatever we choose here. Now when I'm drawing this, I put everything that's in the brackets will be attached to the metal. And like I said, I don't really care about the arrangement. But if it's tetrahedral, I'll always draw it this way with these 2 in the plane, this one sticking back and being represented by a dashed line, and this one sticking forward being represented by a wedge. And on the outside we've got 2 potassiums, and they're going to be positively charged, and there's one for each of those. Alright, now let's take a look at how we get the charge on the chromium central atom. And we'll do that by looking again at the charges of what's connected here and the charge of what's in here. Now potassiums are 2+. What that means is that everything on the outside is 2+, which means this is going to be 2 negative. So the chromium plus the I plus the F plus the Br plus the Cl all has to add up to -2. Now remember, this is 2 positive, so whatever's in here has to be all add up to 2 negative. Now from our table we know that each of these has a -1 charge, so chromium plus -1 plus -1 plus -1 plus -1 equals -2, and chromium is going to end up having to be a +2 charge to make all that work. So that's where we get the 2 plus from on the chromium. To draw an isomer, what we're observing here is we have 4 different things attached to the chromium atom, which means that it is okay to do a stereoisomerism on this. It's tetrahedral, 4 different things attached. And to draw a stereoisomer, all I'm doing is just drawing the mirror image of this compound. And you can see what I've done is I've drawn the I and the F out here, and there they are there, so it's just a mirror image of that. And this Br is sticking back and this Cl is sticking to the front. I'll show you how to do that just so you can see it. Alright, so going back to the original compound. So I'm just copying this directly as it appears. The Br is sticking back and this Cl is sticking out to the front. And so we've got a wedge there. And like I said earlier, it doesn't really matter if they're in this order or not. They can be in any of these and it's still going to be correct. Now to draw the mirror image, I just have the Br sticking like that, have the Cl sticking like that. And as I hopefully convinced you earlier, these two are different because they've got 4 different things attached. We turn around, we can't make these line up, and that would be how you would draw the mirror image, at least of the central part with the with what's on the metal part. Alright, so going back to here, you can see that we've got this one, which is going to be the mirror image, and we've already established that those are different. Next, we take a look at the periodic chart, and we'll look at the, see if we've got it here. Right, so we've got chromium is chromium without the charge on it. We've got the argon, 4s2, 1, 2, 3, 4, so it's Ar, 4s2, 3d4. That's what chromium is. Now chromium 2 plus is going to be chromium with 2 less electrons. As I said earlier, see, s electrons are the first to go, so we lose those 2, and that's going to leave us with Ar, 3d4. So we're going to be left with just 4 electrons on Cr2 plus. And when we put these in, we have to first of all recognize it's going to be tetrahedral, and tetrahedral has this arrangement where we've got the dx squared minus y squared and dz squared down the bottom, and these 3 along the top. We also have to look at whether or not this is going to be a strong or a weak field situation. So we take a look here and we can see that since we've got F, Cl, Br and I, those are all going to be weak fields, so we're looking at a small difference in energy between the 2 layers of d orbitals here, and that means that when we put the electrons in, the 4 unpaired electrons, we put 1 in here and 1 in here, and since these are almost the same energy, we have to put 1 in here and 1 in here as well, and that means it's going to be a weak field, high spin, 4 unpaired electrons.